Climb inside this cramped steel coffin. Feel the weight of 45 tons pressing down through narrow treads. Your hands grip controls that respond like molasses in winter. The engine roars behind you, a temperamental beast that could die at any moment. Welcome to the Panther, Germany's so-called superior tank, the same machine that broke down more often than it fought. The same vehicle that spent more time in repair shops than on battlefields. What Allied tankers discovered inside these captured German marvels would shatter every assumption about tank warfare and change how we understand one of history's greatest engineering debates. December 1944, the snow-covered forests of the Ardennes. American tank crews huddled in their Shermans, watching German armor pour through the mist. Panthers, the sleek predators of the battlefield. 45 tons of sloped armor and a 75mm high-velocity gun. Every American tanker had heard the stories. One Panther could take on 5 Shermans. The German tank's frontal glacis armor was 80mm thick at 55 degrees, providing effective protection equivalent to 139mm. Its turret front measured 100mm. Its Quak K-42L-70 gun could penetrate a Sherman from over 2,000 meters away. American tankers called their own vehicles Ronsons, after the cigarette lighter. Lights, every time, they said grimly. The crews climbing into their 33-ton Shermans that frozen morning knew the numbers. They knew the Panther outgunned them. They knew its armor could shrug off their 75mm rounds from the front. They knew that in a straight fight at long range, they were outmatched. The German tankers knew it too. They had been told their Panthers were invincible, that American tanks were inferior in every way. Their propaganda films showed Panthers crushing Sherman after Sherman, German steel triumphant over American. Mass production. The Panther had been designed specifically to counter the Soviet T-34. After German forces encountered T-34s during Operation Barbarossa in 1941, particularly at the Battle of Mtsensk in October 1941, German High Command immediately dispatched a Special Armor Investigation Committee. The Panther Commission formed in November 1941. Mann's design was selected in May 1942. First prototype appeared in September 1942. Production began January 1943. On paper, it was perfect. The ultimate medium tank. Nearly every technical specification favored the German machine. But something strange started happening as American forces pushed deeper into German territory. Tank recovery teams began finding abandoned Panthers. Not knocked out by enemy fire, not disabled by mines, simply abandoned by their crews. Engines cold, fuel tanks still containing diesel, transmissions locked up. Final drives shattered. Some Allied forces did capture and attempt to use Panthers. The British Coldstream Guards famously operated a Panther they named Cuckoo during fighting at Geitsteren Castle in late 1944 and Operation Blackcock in January 1945. Canadian forces captured an intact Panther in Italy in October 1944, called it the Deserter, and used it in multiple assaults before sending it for study. Polish resistance fighters captured 2 Panthers during the Warsaw Uprising in August 1944. They used them to destroy German machine gun nests and to liberate the Gensioka concentration camp, freeing 348 prisoners. But within days, both Panthers were immobilized due to lack of fuel and batteries and had to be set on fire to prevent recapture. The pattern was consistent. Captured Panthers could fight brilliantly for short periods. Then they broke down. The British, who built 9 Panthers post-war using German parts and technicians, tried to conduct standard acceptance trials in 1947. They could not complete the trials. The Panthers kept breaking down. The British report concluded that very little information of any value was obtained due to the general mechanical unreliability of the Panther. The French army, which operated Panther units post-war using captured vehicles, conducted the most thorough evaluation. Their 1947 technical report titled Le Panther stated directly, "The truly weak spot of the Panther is its final drive, which is of too weak a design and has an average fatigue life of only 150 kilometers. Let that sink in. 150 kilometers. Less than 100 miles before the final drives, the units that transferred power from the transmission to the tracks needed complete replacement. German wartime documents confirmed this catastrophic failure rate. General Guderian wrote in June 1944, "The lifespan of the Panther's motors, 1,400 to 1,500 kilometers, is significantly higher than the Panther's final drives. A solution to the final drive problem is urgently needed." An Eastern Front report from March to April 1944 documented that since the 1st of March, 13 final drives were replaced in 30 Panthers. A January 1945 Panzer Commission report listed 370 defective final drives from Panthers requiring replacement. Half of all Panthers abandoned in Normandy showed final drive failures as the primary mechanical issue. The technical cause was well understood. Mann's original design called for epicyclic planetary gearing. This was changed to double spur gear system due to gear-cutting machinery shortages in German industry. The double spur gears had inherently higher internal impact and stress loads. Here was the fatal flaw. The Panther's drivetrain had been designed for a 30 to 35-ton tank, but Hitler demanded extra armor and a heavier gun during development. The final production Panther weighed 45 tons. The final drive housings, designed for a lighter vehicle, simply could not handle the actual combat weight. The housings flexed under load, the gears inside bound up, destroyed themselves. Sherman final drives, by contrast, could operate for thousands of kilometers without major maintenance. French operational experience from 1946 to 1950 with their captured Panther units confirmed the 150-kilometer failure rate repeatedly. The Maybach HL230 engine, while powerful at 690 horsepower, suffered chronic reliability problems. During Operation Citadel at Kursk in July 1943, Panzer Abteilung 54 experienced 20 fuel pump failures by July 8. Fuel leaks from these failures caused 3 Panthers to become total losses due to engine fires. 2 Panthers from the initial deployment burned out from engine fires just getting off the trains before the battle even began. Documented Maybach engine problems included cylinder head gasket failures, connecting rod breakage, oil pump driveshaft breakage, engine fires from oil leaks onto hot exhaust manifolds, cooling fan drive bearing failures, and chronic overheating. The Germans derated the engine from 3,000 rpm to 2,500 rpm in November 1943 to extend engine lifespan. This reduced maximum speed from 34 miles per hour to 28 miles per hour and power output from 700 to 580 horsepower. Even after these derating measures, average Maybach engine life in Panthers was only 1,000 kilometers, according to the French post-war technical report, with maximum life reaching 1,400 to 1,800 kilometers in some cases. The Panther's turret traverse system added another layer of complexity. Early AUSF-D models used a single-speed hydraulic system requiring approximately 60 seconds for a full 360-degree rotation. Later, OSIF A and G models featured selectable high and low gear ratios. At 2,500 rpm in high gear, the turret could traverse in 17 to 18 seconds. At low RPM or in low gear, traverse time extended to 60 to 93 seconds. The system's performance varied constantly with engine speed. If the engine died, the turret could not traverse at all. The Sherman, by contrast, used an independent auxiliary electric motor. The Sherman's turret always rotated in 15 seconds regardless of engine speed. The commander could traverse the turret even with the main engine off using the backup generator. This consistency provided enormous tactical advantages. The Panther's theoretically faster traverse at optimal engine speed was meaningless when mechanical failures stopped the engine, or when tactical situations required turret movement while the engine idled. The 7-speed manual transmission was stiff and difficult to shift. Every gear change was a battle. Sherman transmissions were smooth and nearly automatic in operation. The Panther's narrow track width, despite good ground pressure on paper, meant less actual contact with soft ground. In mud or snow, Panthers frequently became stuck. Their excellent cross-country performance applied only to firm, dry terrain. The Sherman's wider tracks provided superior real-world traction in varied conditions. Crew ergonomics in the Panther were poor. The interior was dark and cramped. The gunner's position was more confined than in a Sherman. The loader had to reach across the large gun breech in awkward positions to access ammunition scattered around the fighting compartment. The Sherman's ammunition storage featured ready racks within easy reach of the loader. Everything was organized logically. American automotive engineers had designed the Sherman using the same human factors principles they applied to automobiles. Make it easy for the operator. By March of 1945, the complaints from American tankers about facing Panthers and Tigers had reached General Eisenhower repeatedly. He wrote to the commanding generals of the 2nd and 3rd Armored Divisions, asking for detailed assessments. General White, commander of 2nd Armored Division, prefaced his reply by asking Eisenhower to make allowances for the traditional enthusiasm displayed by the American soldier when given the opportunity to express himself regarding any possible shortcomings in his equipment. General Collier, commander of Combat Command A of 2nd Armored Division, provided a detailed assessment. The consensus of opinion of all personnel in the 66th Armored Regiment is that the German tank and anti-tank weapons are far superior to the American in the following categories: superior flotation, greater mobility, better gun sights and higher velocity guns, smokeless powder that made German tanks harder to spot, better sloped armor, and better silhouette. Collier then contested Eisenhower's rationalization that American equipment limitations were justified by shipping distances. The fact that our equipment must be shipped over long distances does not, in the opinion of our tankers, justify our inferiority. This was March 1945. The war in Europe would end in May. Eisenhower replied immediately, "I feel that your conclusions should go at once to the War Department, and I am sending them on to General Marshall without delay. Too late for any changes to affect the outcome." But these documented assessments reveal that American tankers clearly recognized the Panthers' advantages in direct combat. They wanted better tanks. They were not blind to the Sherman's limitations. Yet they won anyway. Not despite the Sherman, but because of what the Sherman represented. A complete weapon system optimized for total war. Between June and December 1944, the 12th Army Group lost more than 2,000 medium tanks, mostly Shermans. These losses shocked the American public when soldiers' letters home and press reports revealed the scale of tank casualties. In January 1945, New York Times correspondent Hanson Baldwin wrote critical editorials urging congressional inquiry into American tank adequacy. The Army leadership responded with articles defending the Sherman. Major General Levin H. Campbell, Jr., Chief of Ordnance, released Eisenhower's letter to diffuse further criticism. After the war, General Marshall tried to explain American tank performance, acknowledging that from summer 1943 to spring 1945, German Tigers and Panthers outmatched Shermans in direct combat. But Marshall's explanation emphasized that American doctrine never intended for medium tanks to fight heavy tanks alone. Tank destroyers, artillery, and air support were meant to neutralize heavy armor, while medium tanks performed their primary role of exploiting breakthroughs and supporting infantry. The Sherman's combat record, examined beyond individual engagements, demonstrates overall effectiveness. American and British forces landed in Normandy in June 1944. By May 1945, 11 months later, Allied armies had advanced from the French coast to Berlin, conquered Germany, and ended the war in Europe. German forces equipped with technically superior armor could not stop this advance, not because Panthers and Tigers were ineffective in battle, they were deadly when they fought, but because they could not fight consistently enough to matter strategically. A tank that breaks down before reaching battle provides zero combat power. A tank immobilized by lack of fuel contributes nothing. A tank awaiting spare parts that never arrive becomes a stationary pillbox. Strategic effect requires sustained operations over time and distance. The Sherman provided sustained operations. The Panther did not. The Sherman succeeded because it prioritized the right factors, not gun penetration at maximum range, not armor thickness in frontal engagements, but reliability, maintainability, crew survivability, production capacity, logistical sustainability, and tactical flexibility. Consider the Sherman's 5-man crew layout. Commander, gunner, loader, driver, assistant driver, who also operated the bow machine gun. The crew positions allowed efficient operation and good crew coordination. Multiple escape routes included a large belly hatch, side hatches, and turret hatches. When a Sherman was hit, crews had excellent chances of escaping. The British, after studying captured Tiger 131, used its technical details to help design the Sherman Firefly with the 17-pounder gun. Sherman variants addressed different tactical needs. The M4A 3E2 Jumbo featured 102mm glacis armor and 152mm turret front armor. Fisher Tank Arsenal produced 254 Jumbos from May to July 1944. These were deployed as breakthrough tanks to lead assaults. The wet ammunition storage system, introduced in Sherman production, placed ammunition in water glycol jacketed bins. This reduced fire probability when penetrated from 60 to 80% down to 10 to 15%. This single improvement saved thousands of crew lives. The 76mm M1 gun, introduced in January 1944 and first seeing combat in July 1944 during Operation Cobra, provided improved armor penetration. However, the 76mm gun had significantly worse high-explosive performance than the 75mm. The 75mm M48 HE round produced 950 effective fragments in a 20-foot radius, according to U.S. Army Technical Manual 9-1907. The 76mm M1 produced only 560 fragments. The reduction in HE effectiveness was a real tactical limitation that many units preferred to avoid. American tankers understood that tanks fought infantry far more often than they fought other tanks. High explosive effectiveness mattered more in most combat situations than armor-penetrating capability. The Panther's 22PA-42 L-70 gun, optimized for anti-armor performance with its high velocity and long barrel, fired a weaker HE shell compared to lower-velocity weapons. High-velocity long-barrel guns sacrifice explosive effectiveness for armor penetration. You cannot optimize for both simultaneously. Israeli forces recognized the Sherman's fundamental soundness. They modified, captured, and purchased Shermans extensively. The M50 Sherman, with a French 75mm gun and Continental R975 engine, served from the 1956 Suez Crisis through the 1967 Six-Day War and the 1973 Yom Kippur War. The M50 Continental Mark I retired in 1972. The M50 Cummins Mark II served into the late 1970s. The M51 Sherman mounted a French 105mm gun. It served from 1965 into the early 1980s. Israeli M51s successfully engaged modern Soviet T-54, T-55, and T-62 tanks, using 105mm heat rounds. Israel sold 75 M51s to Lebanese militias in 1976 and over 100 to Chile, which used them until 1999 and kept some in reserves until 2006. This operational longevity from World War II through the 1970s and 80s demonstrates the Sherman's fundamental design, soundness, and adaptability. Now consider the Panther's systemic failures. Production totaled approximately 6,000 vehicles between January 1943 and March 1945. Not 9,000 as commonly stated. Multiple authoritative sources confirm 6,000 as the accurate total, with some sources citing specifically 5,964 built. Peak monthly production reached 380 in July 1944, but averaged far lower. Frontline combat strength peaked on September 1, 1944 at 2,304 tanks. But that same month, a record 692 tanks were reported lost. The last operational report, dated March 15, 1945, lists only 361 operational out of 740 Panther tanks total. Only 49% operational at war's end. Allied bombing targeted Panther production facilities. Daimler-Benz was struck on August 6 and August 23, 1944. MAN was bombed on September 3, October 3, October 19, 1944, then again on January 3 and February 20 to 21, 1945. These raids forced spare parts production to plummet from 25 to 30% of tank production in 1943 to only 8% in late 1944. Panthers in the field had to be cannibalized for parts to keep others running. The lack of spare parts compounded mechanical reliability problems. German crew training quality declined severely as the war progressed. Historian Stephen Zaloga observed that the Panthers' disappointing performance in the Ardennes against American Shermans, despite superior technical specifications, resulted from poor crew quality by this point in the war. Most Panther crews were inexperienced with minimal training. Lack of training exacerbated the Panthers' technical weaknesses. The combination of poor powertrain durability, lack of fuel, lack of spare parts, and inexperienced crews resulted in many Panthers breaking down and being unable to be recovered or repaired. The French 1947 report noted that poor training of drivers was a principal cause of Panther mechanical defects. The battalion has received drivers who are operating a Panther for the first time. Tanks are being written off for quite minor technical problems. Fuel shortages crippled German armoured operations. Panthers consumed massive amounts of fuel. German logistics could not sustain fuel supplies to forward units. Soviet tanker Dmitry Loza, hero of the Soviet Union, commanded American-supplied Shermans on the Eastern Front. He documented his experiences in the book Commanding the Red Army's Sherman Tanks. In an interview, Loza stated directly, "The service life of the Sherman track was in excess of 5,000 kilometers. He praised Sherman reliability extensively, noting the auxiliary gasoline engine for charging batteries that eliminated the need to run the full 500 horsepower main engine. He commended superior American armor quality with no interior spalling, comfortable crew stations, and general mechanical reliability. He noted the Sherman drove like a car on hard surfaces, and our T-34 made so much noise that only the devil knows how many kilometers away it could be heard." The Sherman's cost efficiency enabled mass production. Initial M3 and early M4 Chrysler contract prices in 1940 to 1942 were $33,000 to $33,500. Later variants ranged from $44,556 to $64,455 depending on model. Official U.S. Army catalog prices in August 1945 listed most Sherman models at $44,000 to $55,000. Total Sherman production reached 49,324 units from 1942 to 1945, not 50,000 as commonly rounded, but 49,324 documented units. American industry produced these vehicles across multiple manufacturers using standardized parts and efficient assembly methods. The Panther's base cost was 117,100 Reichsmarks excluding armament and radio. With the Quip K-42 gun and equipment, combat-ready cost reached approximately 143,912 Reichsmarks. German industry struggled to produce even 6,000 Panthers despite enormous effort. American doctrine emphasized combined arms integration. Shermans operated with infantry, artillery, tank destroyers, and air support. American commanders understood that tank versus tank battles were relatively rare. Most tank combat involved supporting infantry, destroying fortifications, and engaging soft targets. The Sherman's reliable mobility and excellent HE performance made it ideal for these missions. American tank destroyer battalions equipped with M10, M18, and M36 tank destroyers provided dedicated anti-armor capability. The M36 with its 90mm gun could penetrate Panther armor more effectively than Sherman's. During the Battle of the Bulge, M36 equipped battalions, including the 610th, 703rd, and 740th Tank Destroyer Battalions, proved highly effective against German armour. 4 M18s, along with M4 Shermans and infantry from 10th Armoured Division, occupied Noville north of Bastogne and stopped a German armoured attack with flank fires, destroying 30 heavy tanks, including Panthers and Tigers. The Battle of the Bulge in December 1944 and January 1945 tested American armour doctrine under the worst conditions. Hitler's Ardennes offensive launched on December 16, 1944, with approximately 1,500 tanks and assault guns in 24 divisions, including 10 Panzer divisions. The main thrust fell on the 99th and 2nd Infantry Divisions. German forces achieved surprise and initial success. American units, including the 740th Tank Battalion, scrambled to respond. Men pieced together damaged tanks from depot stocks, sometimes finding dead crews still inside vehicles that smelled of death. They managed to assemble 3 M4 Sherman tanks and 1 M36 tank destroyer. On December 19th, this small force engaged elements of SS Lieutenant Colonel Joachim Peiper's battle group, equipped with Panthers and King Tigers at Stoumont. The improvised American tank force knocked out 3 Panthers, helping halt Peiper's spearhead. Throughout the Bulge fighting, American tank destroyers proved their value. Towed anti-tank guns were ineffective in the cold, wet weather and rough terrain. Throughout First Army, 3/4 of towed tank destroyers lost were total losses. The 801st Tank Destroyer Battalion, equipped with towed guns, lost 17 guns in just 2 days. The 644th Tank Destroyer Battalion, equipped with M10 self-propelled guns fighting alongside them, found ideal opportunities for close-range ambushes and claimed 17 German tanks in the same period. The contrast convinced Eisenhower to approve conversion of all remaining towed units to self-propelled guns in January 1945. The M36, just entering service when the offensive began, proved highly effective throughout the Ardennes campaign. Its 90mm gun, the same armament carried by the M26 Pershing heavy tank beginning to reach frontline units, could engage Panthers and Tigers on more equal terms. American logistics enabled sustained operations. Sherman engines used readily available gasoline. Spare parts flowed continuously from factories to frontline units. Maintenance could be performed by moderately trained crews. Battle-damaged Shermans were recovered, repaired, and returned to service rapidly. The U.S. 3rd Armored Division entered combat in Normandy with 232 M4 Sherman tanks. During the entire European campaign, the division had approximately 648 Shermans completely destroyed in combat and another 700 knocked out, repaired, and returned to operation. This 580% loss rate sounds catastrophic, but it demonstrates the Sherman's greatest strength: the ability to be produced in such numbers that losses could be continuously replaced, the ability to be repaired and returned to service, the logistics system that kept replacement tanks flowing forward. German armoured divisions, by contrast, saw their strength decline throughout the campaign as losses could not be replaced. The Battle of Arracourt in September 1944 demonstrated American tactical superiority despite technical inferiority. The 4th Armoured Division's 37th Tank Battalion, commanded by Lieutenant Colonel Creighton Abrams, operating from his Sherman Thunderbolt, engaged German forces including newly arrived Panther-equipped units. Abrams went through 7 different tanks during the war, but always commanded Shermans. At Arracourt, his battalion lost 14 Shermans while destroying 55 Panthers and Tigers. General Patton called Abrams the world champion tank commander. The engagement demonstrated that properly employed Sherman tactics, utilizing terrain, combined arms, and aggressive maneuver, could defeat technically superior German armor. The Sherman won World War II. Not alone, but American armored divisions equipped with Shermans spearheaded the breakout from Normandy, the drive across France, the crossing of the Rhine, the conquest of Germany. They accomplished this against German forces equipped with Panthers, Tigers, King Tigers, and Panthers. Technically superior German armor could not stop American armored operations because wars are not won by technical specifications alone. Logistics wins wars, reliability wins wars, production capacity wins wars, combined arms integration wins wars, crew confidence wins wars, adaptable doctrine wins wars. The Sherman embodied all these factors. The Panther embodied impressive specifications but failed at systemic integration. When Soviet forces captured Panthers and attempted to use them against Germans, the vehicles performed briefly, then broke down. A February 1945 Lower Silesian offensive saw one captured Panther with an experienced crew from 4th Tank Corps under command of hero of the Soviet Union Lieutenant Nikolai Ivanovich Ageev, used in a reconnaissance mission. At dusk, the tank passed through forest, attacked from the flank, and destroyed 3 enemy Panthers. During retreat to Soviet positions, it was hit by German artillery and damaged. After the battle, the tank was written off due to lack of spare parts and maintenance problems. Even when operated by skilled Soviet crews, captured Panthers proved unsustainable. The systematic analysis of tank effectiveness must account for the entire weapon system: design, production, logistics, maintenance, doctrine, crew training, tactical employment, and sustainability. The Panther excelled at a narrow set of specifications: gun penetration at long range, frontal armor protection in direct engagement, speed on good terrain. But it failed catastrophically at reliability, maintainability, production efficiency, logistics sustainability, crew ergonomics, and operational availability. The Sherman provided adequate performance in gun and armor specifications while excelling at reliability, maintainability, production efficiency, logistics sustainability, crew ergonomics, escape provisions, and operational availability. In total war, adequate technical specifications combined with superior systemic factors defeat superior technical specifications combined with inferior systemic factors, every time. The lesson transcends World War II. The lesson transcends tank design. Any weapon system, any tool, any technology must serve its users under real-world conditions, must function reliably when needed most, must be maintainable with available resources and infrastructure, must account for human factors in operation and maintenance, must integrate effectively with other systems, must align with operational doctrine, must be sustainable through the logistics chain, must be producible in quantities that meet demand. Technical excellence that ignores these factors produces expensive failures that look impressive on paper but collapse under operational stress. Practical adequacy that embraces these factors produces war-winning tools that perform reliably under the worst conditions. The Panther's development, rushed into production after encountering T-34s, never achieved the maturity needed for reliable field operations. Its combat debut at Kursk in July 1943 was disastrous with widespread mechanical failures. Improvements reduced but never eliminated the fundamental design flaws. The final drive problem, rooted in weight growth beyond original design parameters, was never solved. Engine reliability improved somewhat, but remained poor compared to Allied tanks. The complexity of the design exceeded German industrial capacity to manufacture with adequate quality control, especially as Allied bombing damaged factories and disrupted supply chains. The Panther represented German engineering's tendency toward over-optimization for specific parameters at the expense of overall system effectiveness. The Sherman represented American industrial pragmatism. Design for manufacture. Design for maintenance. Design for logistics. Design for the crew. The Sherman was never intended to be the best tank by any single metric. It was intended to be good enough at everything while being excellent at the factors that mattered most for sustained operations: reliability, maintainability, producibility. The automotive industry's mass production expertise, applied to plate, tank manufacturing, created a weapon system that could be built by the thousands and sustained across global supply lines. Ford, Chrysler, General Motors, American Locomotive Company, Baldwin Locomotive Works, Lima Locomotive Works, Pacific Car and Foundry Company, and others produced Shermans using standardized components and efficient assembly methods. The last Panther rolled off production lines in March or April 1945. By then, many were being abandoned before even reaching combat units due to lack of fuel and trained crews. The last Shermans rolled into Berlin in May 1945 as the war in Europe ended. Israeli-modified Shermans fought in the Yom Kippur War in October 1973, nearly 30 years after the war ended. This operational longevity gap of 3 decades between the Panther's extinction and the Sherman's continued evolution illustrates which design philosophy proved more sustainable. The Panther was a developmental dead end. No post-war tank designs borrowed significantly from it. The Sherman influenced post-war tank development globally because its fundamental approach, prioritizing reliability and maintainability alongside combat capability, represented the correct balance for practical military operations. American tankers in 1945 understood these truths through direct experience. They faced Panthers in combat. They recovered abandoned Panthers from the battlefield. Some units evaluated captured Panthers. They recognized the Panther's advantages in direct engagements. But they also recognized the Panther's fatal weaknesses in sustained operations. They understood that a tank unable to reach the battlefield due to mechanical failure provides zero combat power. They understood that a tank burning through fuel faster than logistics can supply becomes immobile. They understood that a tank requiring specialized parts unavailable in the field becomes scrap metal. They understood that a tank with inadequate crew escape provisions becomes a death trap when hit. The Sherman's nickname as Ronson Lighter reflected the real fire danger from ammunition stowage in early models. This was a serious problem that cost lives. American engineers responded with wet ammunition stowage, dramatically reducing fire risk. German engineers made no equivalent improvements to Panther survivability. The Sherman's relatively thin armor was a real vulnerability in direct tank combat. American doctrine responded by emphasizing combined arms, avoiding frontal engagements when possible, and using tank destroyers for anti-armor missions. German doctrine emphasized increasingly heavy armor on new tank designs, resulting in vehicles too heavy for their drivetrains and too expensive to produce in adequate numbers. Different approaches, different results. The American approach won. The statistical evidence is overwhelming. 49,324 Sherman tanks produced, 6,000 Panthers produced. Sherman operational availability rates remained high throughout the war. Panther operational availability declined to 49% by March 1945. American armored divisions maintained combat effectiveness from Normandy to Berlin, despite heavy losses because the logistics system continuously replaced losses. German armored divisions declined in strength throughout the campaign as losses exceeded replacement capacity. American combined arms doctrine integrated tanks with infantry, artillery, air support, and specialized vehicles effectively. German doctrine increasingly relied on tanks alone to compensate for declining infantry and artillery capability. Understanding the Sherman success requires examining American industrial mobilization. When war began, American automotive manufacturers converted production lines from civilian vehicles to military equipment. Ford's River Rouge plant, Chrysler's tank arsenal, General Motors facilities, all transformed to produce tanks using assembly line methods perfected for automobile production. Workers who had built cars applied the same efficiency principles to building tanks. Standardization of parts across manufacturers meant a transmission from one factory fit a hull from another factory. A gun mount from Fisher Tank Arsenal matched a turret from American Locomotive Company. This interchangeability, commonplace in automobile manufacturing but novel in military production, enabled unprecedented production rates and simplified field maintenance. The Sherman design prioritized ease of manufacture. Curved armor plates, while more resistant to penetration, require expensive dies and specialized presses. The Sherman used largely flat armor plates that could be cut and welded efficiently. The cast turret could be produced in large foundries using techniques adapted from civilian heavy industry. The suspension system used vertical volute spring units, simple and reliable, that could be manufactured by companies with no previous military experience. Every design choice reflected the priority of mass production without requiring specialized tools or techniques. Training new tank crews in the Sherman took approximately 13 weeks at armored training centers. The layout was intuitive for men familiar with automotive equipment. The controls responded predictably. The maintenance procedures, documented in clear technical manuals, could be learned by mechanics with basic automotive background. German Panther training required longer periods and more specialized instruction due to the vehicle's complexity. As German losses mounted and training time shortened, crew quality declined. American training pipeline, by contrast, maintained consistent standards throughout the war, producing adequately trained crews at the rate operations demanded. The Sherman's maintenance advantages became apparent in sustained operations. An average Sherman engine change required 8 to 10 hours with a trained crew and proper equipment. The power pack, engine and transmission together could be removed and replaced as a unit. Armored divisions carried spare power packs on trucks following advancing tank columns. A disabled Sherman could be back in action within hours. Panther engine removal required significantly more time and specialized equipment. The engine and transmission were separate units, each requiring individual removal procedures. Field maintenance of Panthers often proved impossible, requiring tanks to be towed long distances to depot-level facilities. Many Panthers were abandoned after relatively minor failures because repair in the field was impractical. Sherman track replacement could be accomplished by the crew in the field in 3 to 4 hours per side. The track blocks were relatively lightweight and could be handled by 2 men. Panther tracks were heavier and more difficult to work with. The interleaved road wheel system, while providing excellent ride quality, meant that if an inner road wheel was damaged, multiple outer wheels had to be removed first to access it. In winter conditions, mud and snow froze between the interleaved wheels, immobilizing Panthers until extensive de-icing efforts were completed. Shermans with their simpler suspension and independently mounted road wheels did not suffer this vulnerability. The logistics tail for Sherman operations was extensive but sustainable. Each armored division required thousands of tons of fuel, ammunition, spare parts, and supplies monthly. American logistics units delivered these supplies reliably across growing distances as armies advanced through Europe. The Red Ball Express, a truck convoy system, delivered 7,000 tons of supplies daily at its peak. Liberty ships brought material from American factories across the Atlantic. The logistics system worked because it was planned, resourced, and executed as an integrated whole. German logistics, by contrast, collapsed as Allied bombing destroyed rail networks, fuel production facilities, and transportation infrastructure. Even when Panthers were mechanically sound, lack of fuel immobilized them. Sherman fuel consumption, while substantial, remained within logistical sustainability. Combat operations consumed fuel at high rates, but American logistics could deliver adequate supplies continuously. Panthers consumed fuel at similar or higher rates, but German logistics could not maintain supply. The difference was not vehicle consumption, but logistics system capacity. American logistics was built to support mechanized warfare on a global scale across ocean supply lines. German logistics was designed for relatively short campaigns within Europe and collapsed under sustained operations and Allied interdiction. The Sherman succeeded because it was designed, produced, and employed as part of a complete military system. The Panther failed because it was designed as a technically superior weapon without adequate consideration for the system required to sustain it in combat. Wars are fought by systems, not by weapons. The side with the better system wins, even when the enemy has better weapons. The United States in World War II built and sustained a military system capable of projecting power globally, supplying forces across oceans, maintaining equipment in harsh conditions, training replacement personnel continuously, and adapting doctrine to changing circumstances. Germany built increasingly sophisticated weapons that its industrial base could not produce in adequate numbers, its logistics network could not sustain in the field, its training pipeline could not provide adequate crews for, and its tactical doctrine could not employ effectively given declining resources. Post-war analysis by military professionals confirmed these conclusions. The French army, operating captured Panthers from 1946 to 1950 in the 501st and 503rd Armoured Regiments, documented every mechanical failure and operational limitation. Their 1947 technical report, Le Panther, became the definitive assessment of the vehicle's true performance under sustained military operations. The report confirmed the 150-kilometre final drive life, the 1,000-kilometre engine life, the maintenance difficulties, the fuel consumption, the crew discomfort, the tactical limitations. French engineers and tankers, initially impressed by the Panther's specifications, concluded that the Sherman was the superior combat vehicle when all factors were considered. They noted that while certain Panther features were admirable, particularly the gun and optical equipment, the overall package was unsuitable for sustained military operations. The British post-war evaluation reached similar conclusions. British forces captured numerous Panthers during the campaign in northwest Europe. After the German surrender, British authorities commandeered a German Panther assembly facility at Hanover and forced completion of 9 additional Panthers using existing components and German technicians. These 9 British-built Panthers, completed in spring 1946, were intended for comprehensive testing. Standard British armoured vehicle acceptance trials were conducted on 2 Panthers and 2 Jagd Panthers. The trials had to be halted when the last working Panther damaged its transmission during a hill climbing test. All other Panthers had already been cannibalized for spare parts or had broken down from mechanical failures. The conclusive report, dated February 1948, stated that very little information of any value was obtained, noting the reason as the general mechanical unreliability of the Panther and Jag Panther tanks. Britain, like France, found that captured Panthers were interesting technically but useless operationally. American testing at Aberdeen Proving Ground in Maryland examined captured Panthers, though detailed public reports comparable to the French assessment have not been widely published. Multiple Panthers were documented at the U.S. Army Ordnance Museum at Aberdeen. The facility specifically examined captured enemy equipment from every battlefront. American engineers recognized the Panther's advanced features, but also documented its numerous flaws. The knowledge gained influenced post-war American tank development, though not by copying Panther systems. Rather, American engineers learned what not to do. How over-optimization for specific parameters creates systems that fail under operational stress. How complexity without corresponding reliability produces unusable weapons. How impressive specifications mean nothing if the vehicle cannot be sustained in combat. The developmental dead end of the Panther contrasts sharply with the Sherman's evolutionary success. Many World War II weapons systems continued in service for decades or influenced post-war development significantly. The German Me-109 fighter was produced and developed by Spain and Czechoslovakia into the early 1960s. Mauser rifles remained in service with numerous armies post-war, but the Panther vanished. No nation adopted it for post-war service once captured stocks and spare parts were exhausted. The Soviets, who captured hundreds of Panthers, used them briefly, then discarded them. Czechoslovakia and other Eastern European nations that operated captured Panthers in the immediate post-war period quickly replaced them with Soviet designs. France and Britain, after thorough evaluation, concluded the Panther was not worth continued operation. The design influenced no subsequent tank development in any meaningful way. The Sherman, by contrast, evolved continuously. The basic M4 platform was adapted for dozens of specialized roles. Tank recovery vehicles, armored personnel carriers, self-propelled artillery, rocket launchers, bridge layers, mine clearers, and flame throwers all used Sherman chassis. The adaptability of the design allowed it to serve in roles far beyond its original purpose. Israeli modifications produced vehicles that fought successfully in the 1960s and 70s against Soviet-designed armor. The M50 and M51 represented comprehensive rebuilds that retained only the basic hull while upgrading every system. These Israeli Shermans mounted French cannons, American or British engines, improved suspension, modernized fire control systems, and enhanced armor. They proved that the fundamental Sherman design was sound enough to accept decades of improvements. The Panther's design allowed no such evolution. Its complexity and tight integration meant modifications were impractical. The vehicle was optimized for its original configuration and could not adapt. The Sherman represents one of history's most successful weapon systems, not because it was perfect, not because it was the best tank by any single metric, but because it was good enough, reliable enough, maintainable enough, producible enough, and trusted enough by the crews who fought in it. That combination of adequate technical capability with superior systemic factors created a weapon that won the war. The Panther represents a cautionary tale about the limits of technical superiority. Impressive specifications matter little when the weapon cannot reach the battlefield, cannot be sustained in combat, cannot be produced in adequate numbers, and cannot be operated effectively by available crews. Technical excellence divorced from systemic requirements produces expensive, unreliable, unsustainable failures, no matter how impressive the design appears on paper. History has delivered its verdict. The Sherman won, the Panther lost, not in any single engagement, but in the campaign that mattered, the production battle, the logistics battle, the sustainability battle, the reliability battle. American tankers understood this. They lived it. They fought in it. They won because of it. 79 years later, the lesson remains clear. Wars are won by systems, not by weapons. The side that builds the better system, even with adequate rather than superior weapons, defeats the side with superior weapons but inadequate systems. The Sherman versus Panther debate ended in May 1945, when American Shermans rolled through Berlin while abandoned Panthers littered the roads behind the retreating German army. The debate never should have existed. The answer was always obvious to those who understood that effectiveness in war is measured not by specifications but by results.